Thank you. So actually, I wanted to start as perhaps it would have been more appropriate as a first lecture because I'm going to be way more elementary than the other speakers, at least at the beginning. And my goal is really what I'm going to talk about is zero knowledge and what it is and why it's interesting. I'll explain zero knowledge through a physical analogy, through the zero knowledge for Sudoku. And this is actually work done a couple of years ago with Ronen Gradwell, Benny Pincus, and Guy Rothblum here. And then I'll talk about new work, applying zero knowledge concepts to physical problems. So it's going to be the complement of the previous one. I'll explain digital zero knowledge using physical analogies, and then I'll show how you can do zero knowledge for physical properties. And in particular for DNA forensic tests, and this is work with Ben Fish and Daniel Freund. Okay, so what is Sudoku? Well, I assume most of you know. It's a puzzle that often appears in newspapers. Not that old. I guess it became popular like 6 or 7 years ago. You have a grid, a 9 by 9 grid. You have to fill in the empty entries in the grid so that every row, every column, and every subgrid contains all the digits 1 through 9. And of course, you can generalize it to an n by n grid when n equals k. And the size of the instance is something like n squared log n. And of course, there's nothing special about the numbers 1 through 9. OK, so now here's the story I'm going to tell you. We have two people, Paul and Veronica. They know of a Sudoku puzzle. And Paul claims that he knows the solution. But of course, Veronica says, oh, yeah, prove it. And he says, I could prove it. I could show you that I know the solution, but I don't want you to ruin it to you. I don't want to tell you how to solve it. You should do it on your own. So how can Paul convince Veronica that he knows the solution, that there is a solution, that he knows the solution, etc.? So this is what zero knowledge, without, of course, ruining the puzzle for her. So first, what we want here is an interactive proof. So an interactive proof is a protocol. It's a probabilistic protocol. Probabilistic meaning that it's not clear exactly. There are a couple of possible messages each side can say. So it's a probabilistic protocol between two parties, prover and verifier. They both know an instance of, in this case, of a problem. And the prover might know a witness or a solution. We often call it a witness. The solution, we call it a witness to the fact that, let's say, there is a solution that he knows it. The players chat, that is, exchange messages. And at the end, the verifier accepts or rejects. This is what an interactive proof is. I didn't say anything about zero knowledge yet. OK, and what the properties we want are completeness. That we want that if the people are following the protocol and the verifier is honest, then he accepts a correct proof. And this basically we want it to happen with probability 1. We want soundness. The probability that the verifier accepts an incorrect proof, we want it to be small. Ideally, of course, we would want it to be 0, but in almost all cases, it's non-zero. It's something small, and we want to make it as small as possible. Actually, we're going to see in this talk one counterexample where it is going to be 0. Now, we want the protocol also to be zero knowledge. So what does it mean for it to be zero knowledge? So it's zero knowledge. It has to be an interactive proof. And the zero knowledge property is whatever the verifier learned from the prover, she could, the verifier, in our case, Veronica is the verifier, Paul is the prover, V and V, P and P. So whatever the verifier learned from the prover, she could have learned by herself. What does that mean? That's that's perhaps the important conceptual step is to phrase this, that whatever she learned from the prover she could have learned by herself, is to say that there exists an efficient simulator that can simulate the conversation without access to an actual prover. If the verifier could have produced the same distribution of conversations as the actual one, then she hasn't learned anything, because she could have simulated the conversation on her own. And the important fact is that there are zero-knowledge proofs for all NP problems. For all problems that can be checked efficiently if you are willing to give away the solution, there are zero-knowledge proofs for all such problems. And that's the amazing fact, GMW 86. And usually when people want to demonstrate it, there are two kinds of things. One is through three-colorability of graphs, another is through Hamiltonicity. And it turns out that for Sudoku, there are proofs that correspond to the three-colorability. You can always reduce it to so first, of course, Sudoku is a problem in NP. It's easy to verify. If I give you a solution to a puzzle, it's very easy. You just have to go line by line, row by row, and subgrid by subgrid, and make sure that the solution is good. So it's also NP complete, but that's not going to matter to us in this talk. So I can demonstrate directly on Sudoku. I have a proof that stems from the three-colorability proof and one that stems from Hamiltonicity. The one that we'll see is probably closer to the Hamiltonicity. Okay. So why is it interesting? Why zero knowledge? So of course I can tell you stories, Paul, Veronica, etc. But there are even deeper reasons than that. One is, for instance, you can take such a protocol and use it to a very practical problem of authenticating your identity. When you go to a car and you want to use your this thing to prove that you're indeed entitled to open the door and start the engine, etc. It's better if you use you want to have some identification protocol, and you can use zero-knowledge proofs in order to get very good identification. Protocols, that is, you prove who you are by proving that you know a certain secret that only you're supposed to know it. So even though you're proving to the car that you are who you claim you are, the car, nobody who has access to the car can actually duplicate your key. So that's certainly a good property to have. I mean, you give it to the garage or whatever, they won't be able to duplicate your key. In particular, what you can use zero knowledge is to force malicious adversaries to act according to the protocol. So you design your protocol so that it works assuming a benign adversary that more or less follows the protocol as it should. And then you compile it using zero knowledge proofs to get a protocol that works even when the adversary is malicious. And the compiled protocol withstands malicious adversaries. Now you can ask what's about Sudoku? What's so special? Well, it has nice properties, and it's educational. Everybody, I guess, knows about Sudoku puzzles, so that's the basic reason. No other reason than that. And of course, that it's fun. Okay, so here is how we'll do it, and you will use a physical, I promise you, we'll use a physical description of the protocol. And I'll say a few words how to do a digital implementation of it, and then I'll do the other way around with forensic evidence. So we're going to use playing cards for a protocol. The messages will basically be playing cards, and to seal a message, to seal a thing, will be turning a card face down, and to reveal it will be to turn it up, to turn it face up. So we are assuming that they're not sending messages, but they are in the same room. We're also assuming that they can shuffle Paul can get a perfect shuffle of his cards. Veronica can make sure that no cards were switched. That is, Paul is doing the shuffling, and he can't. We're assuming that she can make sure that he's not putting in a new card or something like that. That's, of course, if you're into playing poker or whatever, is important property to have, and perhaps it's not so trivial, but we have to assume it. And we're assuming, but more so, we're assuming a more benign adversary than we want. We're assuming that either the protocol works or the cheating player is labeled as a cheater. So perhaps Veronica will learn something she shouldn't have learned, but Paul will know that she didn't act properly and will know not to play with her in the future or something like that. Usually we want her not to be able to do it at all, but for our purposes it will be good enough that if she's a cheater is caught as a cheater. Okay, sometimes it's called a covert adversary, but that's not important. So here is the protocol. Here's a protocol that we'll do the 3 by 3, not the 9 by 9. So here is so what Paul does. He puts he has a solution. He puts the solution in the cards corresponding to the solution on the board. Now what Veronica does is she flips a coin and asks to see either the rows or the columns. And of course, if they're subgrids, it's subgrids. I'm just doing it 3 by 3 in either rows and columns. So Veronica flips a coin and decides whether, it doesn't have to be a fair coin, but for her, from her point of view, it shouldn't be something that Paul can guess ahead of time. She decides to pick either rows or columns. Let's say she decides rows, so the cards are taken row by row, shuffled. They're shuffled, each row is shuffled separately, and then it's revealed, and Veronica has to make sure that each row contains the numbers 1 through 3. Okay, so that's the protocol. Her choice was decide either rows or columns, then gathering the cards, shuffling, and making and open and revealing them, turning them face up. Okay. So that's basically the protocol. It's something you can do. It takes some time. I haven't done it many times, perhaps only once, but I've done it at least once. I have pictures to prove it. So, of course, perhaps it's from the simulation, not from the actual protocol. But it's something you can do. And of course, we need to choose row, columns, or subgrids if we want here. And now, what are the properties of this protocol? Well, completeness, I think it's quite simple to see that we have perfect completeness here. If Paul knows the solution, then he will convince Veronica that the solution is good. By the way, there is something perhaps I didn't say. That for the values that are filled in, where you know what it is ahead of time, of course, that should be that should be face up. If there should be a 5 in a certain place, then of course you show that there is a 5 there. You don't, otherwise there isn't a connection to the actual problem. So don't forget this step. Anyway, so as we said, completeness, we have perfect completeness. Soundness, well, a cheating prover must cheat either in row or in column or subgrid. He can't, if he's good in all of them, then he has a solution. Therefore, he's caught with probability at least 1/3. And in terms of zero knowledge, well, what does V see? What Veronica sees is only some permuted values of the numbers 1 through 9. She gets a random permutation of the numbers 1 through 9 in the columns she does. It's very easy to describe the simulator in this case. You see what she chooses, row, columns, or grids, and then you put, and then you give 9 permutations of the numbers 1 through 9. Now, we can reduce the error. There are ways to reduce the probability, because here we're cheating only with probability 1/3. I'm not going to go into all of them. Certainly, repeating the protocol will reduce the probability of error, but you can have a better analysis of the protocol also and get a better probability than 1/3. But here is an alternative. If we have just one thing, if we have a trusted copy machine, so we need a machine that makes trusted copies. You put in a piece of paper and produces 3 identical copies, or 2 identical copies we need. And it doesn't, what we need is that it wouldn't invent something on its own. And we need also that it wouldn't restore it wouldn't store the copy. That is, it wouldn't store in its own memory what was the document that it was copying. So if we have such a machine, so it's relatively little trust, not zero trust, but relatively little trust, then we don't need any probability of error, because we prepare 3 copies of the solution. The puzzle should be printed on the back. 1 copy is cut along rows, 1 copy is cut along the columns, and 1 copy is cut along the subgrids. And each strip is then cut into cells, and the cells are shuffled or sorted by the prover, and then you verify that all the values 1 through 9 are there. So that's, you get, there is no, by this small trust that we have, the copy machine, we have zero soundness error. So, and we got that by some physical assumption here. You can call it this way. Okay. So this was a physical analogy. How do we actually implement? We can implement them more or less directly by exchanging messages. So Paul and Veronica don't have to be in the same room. And all the things I described before, you can implement using commitments, encryption, and oblivious transfer. You don't really need oblivious transfer for proving zero knowledge. You just need commitments. But perhaps to implement the protocol the way I described it, you do need oblivious transfer. Where is Thomas? Thomas, yeah, okay. So Thomas tells us that we can have lots and lots of oblivious transfers, so we're in good shape. Not to be afraid of oblivious transfers. Anyway, so so what do we usually have? We have some mathematical relation R. The prover and the verifier receive an input X. The prover has a secret input W, or the witness of the solution. The prover wants to convince the verifier that there is a W such as RXW that makes the relation be 1, and that she knows such a W. And the prover and the verifier exchange messages. So that's how a typical digital zero knowledge protocol works. And then the protocol should reveal nothing, even to an adversary, even if the verifier is adversarial. There is a way to simulate her conversation. Okay, so now what I want to say, what I want to talk about is the case, what happens if R is not a mathematical relation, but a physical property. The input X is physical, and R is is a physical object, and R is some physical property of this object. So there is a measurement, and the measurement can convince anyone who can take it that it indeed has the property. So what am I talking? And now the question is, can the prover convince the verifier without revealing any more information about X? Can he convince him that indeed X has the property? Okay, so that's what I mean by physical zero knowledge. So there is the issue, how do we even formalize it? I mean, perhaps I didn't emphasize formalization before, but I promised you I can do it. Here it's not clear. that we can formalize it, and it's indeed some of the things we have to worry about. What exactly is a witness? It's not actually a witness as before. And on the other hand, we have all this well-developed zero-knowledge and secure function evaluation framework, and we want to use it in this case. So what are examples of physical properties? So let's start with a simple example. The Pepsi versus a Coke one. This, I think, is sometimes given also for examples for as demonstrating zero knowledge, but actually I think it particularly demonstrates physical zero knowledge. So what does Alice claim? Alice claims she can distinguish between Coke and Pepsi. And Bob wants to test it. So what does he do? He has a Pepsi can and he has a Coke can, and he chooses one of them at random, puts it in the cup, gives the cup to Alice, and oops, it's the wrong direction, and asks her, what did I give you? Did I give you Coke or did I give you Pepsi? If she's good at it, if she can indeed distinguish, she'll tell him, she'll have the correct value. If not, if she cannot distinguish, well, she can't do better than half. So if we want better probability, we'll repeat it t times. So is this a zero knowledge protocol? It's a question.
You can't prove for sure.
Hmm?
You can't prove for sure. That's true. You can't prove for sure.
Sure. No, right, but for the zero knowledge aspect, does Bob learn anything about Alice? We have to be careful about what happened, for instance, if Bob, instead of giving her either Pepsi or Coke, gives her a mixture and then sees how she reacts. Then he learns something about her that she doesn't. He's willing to believe that she can distinguish Coke and Pepsi, but what about 70% Coke and 25% Pepsi? What does she think it is? Does she think it's Coke or does she think it's Pepsi? This protocol allows him to do such things.
So or give RC and see what she thinks.
Right, or he can give her RC, exactly.
Why not go for the standard example that Bob has, a glass where she really wants to know whether it's Coke or Pepsi?
Pardon?
Like the standard example would be that Bob has a glass where he doesn't know whether he receives it from the outside and he doesn't know whether it's Coke or Pepsi, and then he gives it to him. Right? I mean, that's the standard problem with this kind of problem.
No, but that's not the case. Who gives him it? Who gives him?
This is something that he wasn't.
Pardon?
This is something that he wasn't able to do on his own, right?
Right. No. But the point, what is Alice trying to do? Alice is trying to convince him of a physical property. The physical property is something about her taste buds.
But my point is that it's not, right? Even this contradicts zero knowledge.
What contradicts zero knowledge? Okay. Okay, the man in the middle. Okay, good. Yeah, that he doesn't know, right, yeah. Okay. So this work I mentioned with Daniel Freund and Ben Fish, we suggested the framework for modeling physical zero knowledge and about physical claims, zero knowledge about physical claims, and we explored it in two domains. One is the equality of objects, where the motivation is arms control. Actually, you want you have, let's say, Russia wants to prove to the U.S. that it's dismantling its nuclear warheads. So there are lots of assumptions here, but in particular, there is an assumption that there is a template of the U.S. has a good warhead, a good Russian warhead. Russia is not willing for the U.S. to see what's inside, but as they come into the dismantling factory, they want to convince the U.S., or the U.S. wants to be convinced that indeed the warheads are identical. What's come in is identical to the template that they have, without giving information about their structure. So how can you do that in a zero-knowledge fashion? And this is an actual problem That is, right now there is some solution to it, and the question is whether it's good. And what I'm going to describe in more detail, perhaps, is physical zero-knowledge proofs for DNA profiling. How can you convince that you're not a murderer or whatever? And of course, you can think of other things like paternity tests, etc. Okay, and I should mention that there is work. This original problem was formulated by Glaser, Barak, and Goldstone. I don't think it's Goldstone from the Goldstone Committee. And some of the later work is independent of ours. Okay, so as I said, it's, the problem is inherently physical. It's not that there is the digital analog. There is, we want to prove that an object has a physical property. So it can't be just a completely digital solution. Okay, we can't converting the problem into the digital domain inherently reveals information or like soundness. So we have to do something. So there are all sorts of works in this direction, not a whole lot, but those of you who know distance bounding protocols you want to prove that it's not only you, but that you're close to a certain location. And you can use timing, and again, the motivation is related to cars. You want to prove to the car that not only it's you, but that you're close to the car. And the physical property here is the speed of light that we are using. And this turned out into position-based cryptography, which it's a non-trivial problem, but this is a different direction than I'm going to talk about. And there is the work that I mentioned before by Glaser et al. Okay, so here I'm really going to talk mostly about proofs for DNA profiling, and even there I'm probably not going to get too deep. Let's see, what time is it? Till how much? 20 minutes. Okay, so we'll do something. Okay, so here is the thing. We have a police. The police have a crime scene DNA sample C, and they want to compare it to a suspect DNA sample S. So C, crime scene, S, suspect. Okay? So the police have C, Alice produces S. The suspect produces S. And they want to compare it. They want to compare S to C. And Alice, of course, claims that she's innocent. So she wants to argue that S is not equal to C. So what can we do? What can Alice do? Right now, we know what they do. The police takes the sample from Alice, and they handle both S and C and argue that they are the same. So they certainly have full access to Alice's sample. And we are going to argue that it's not necessary. In particular, it's true, this is, I think, motivated in cases where Alice is not a very strong suspect. Maybe there is a chance that she was around. Perhaps you're want to test the whole village. This is the original example of the usage of DNA profiling was to test the village. And actually, the way the person was caught is because he avoided, because he tried to cheat and use someone else's DNA, and then it came out. So sometimes we can't force someone to give their DNA, or don't want to be in a situation where the whole village is being tested, but perhaps the whole village is willing to prove that their sample is different from the crime scene DNA without giving any more information. Okay, so this is it. How do you prove that you do not match? So here, we do have to go a little into how DNA profiling works. And basically, your DNA profiling compares specific gene regions containing STR sequences, single tandem repeat sequences, things that repeat many times. I'm going to go into more detail. And basically, That depends on the country, the UK, the US, it's a little different. But it's basically there are 13 locations in the chromosome. And you're comparing these locations, you're comparing the two, the crime scene and the suspect, you're comparing them in those locations. And specifically, so a single tandem repeat is something like a short string, like GATA. You know about DNA. It's a string for a letter alphabet. So there is a short string, GATA in this case, that repeats a certain number of times. Let's say n equals 10, n equals 13, or something like that. Now, also it has a certain known region of base pairs. The sequence before this repeat is known, and after. And the way you will identify it is by cutting the DNA in these locations, and then test the length. You'll be able to test. You know these lengths. The thing before it and the thing after it. You know it. Now the only question, the only variability is what is n? How many times does it repeat? Okay, and it can either be, let's say, 10 times or it can be 13 times, and you can test it, and that's what distinguishes individuals. Now there is a further complications of heterozygote versus homozygote. Do you have the same chromosome? Is it identical in both your chromosomes or not? Let's imagine that the problem doesn't exist. Otherwise, the solution becomes more complicated. So a DNA profile is a vector of STR sequence length. So it's a 13 long vector. Let's say, at least in the homozygote case, it's a vector of length 13 of numbers, of integers. And as we said, the primers, you use the DNA primers and the polymerase chain reaction to isolate those sequences and then test them. How do we test them? There are several techniques. It's not that important to us, but there is the way it's usually done is capillary electrophoresis, where the DNA fragments are fluorescently labeled during the PCR. They pass through the tube. Smaller fragments pass faster than larger one. The laser detects the fragments as they pass by because they're fluorescent, and the length of the fragments is deduced from the time it takes to reach the laser. That's all we need, and perhaps more than we need to know about it. So essentially, there are two vectors, and you want to prove that they're not equal. Okay? So here is how we imagine. We imagine that there is a forensic defender team representing the suspect. We call it DEF. And there is the forensic police team, which we call POL, police. And now, yeah?
You assume that the blood, whatever, will sample securely from the suspect?
No, that's a good question. Yeah.
Okay, so
No, that's a good point. It's a good point. Yeah. The police has to be convinced that indeed the blood or the...
also the suspect has to trust the guy with blood.
Well, he was proving that he's different from it. I mean, if they took his own saliva and claimed that it's that's from the crime scene, what can you do? But right. So here, what do we have? There are two tubes, the suspect and the crime scene, and the defender claims that they're not equal. So it's very similar to the Coke-Pepsi thing. If they're not equal, and you have these devices I mentioned before, then you can distinguish between the two. You can say, if you're given a sample from the suspect or the sample from the crime scene, then you can tell which is which. Right? If they're different. And all you need to know is you need to know your own. You just need to know your own sample. If you know your own sample, and you're given either from this tube or from that tube, then you can tell whether whether it's the suspect or whether it's the crime scene.
Haven't we already lost because we've given the police our DNA?
Yeah. That's, yeah. So we're giving them the DNA, we're trusting them a little too much, and that's the part that I'm probably not going to get to. I'll say how you don't need that. But right. So they do exactly as a Coke and Pepsi. Yeah.
One more question. Should it also work the opposite way? Should the suspect be not aware of the DNA from the scene?
Right, that's another problem. That this thing, the suspect learns the DNA from the crime scene. So this is something actually we don't know how to get rid of. This problem. It's a good question. Right. So then it's exactly the same analysis. Oh, I didn't say before how to handle the case where if the police do all sorts of tricks. I didn't mention it with the Coke and Pepsi. But you can use some of the tricks you can use there. You can use them here. Right here, there is the issue what happens if they sneak a third one, like they sneak in the, I don't know, they suddenly the opportunity test, or they sneak in something from a relative. All sorts of things you can do. And then there are also soundness issues. For instance, perhaps there are other ways of distinguishing between the two DNAs. So it's a non-trivial issue. We'll handle some of these questions. Some of them we'll leave open. Okay. So first, what about the police sneaking in a different sample? We use tamper evidence seals. So we seal the tube with something that only if you open it or change it, then it will be evident. So we have to assume that you have such a tamper evidence seal. And they have some random serial pattern that the defender can identify. It must be non-forgeable, at least during the protocol. And one thing about it is that all the PCR reactions, etc., all of them are done in preparation. The only thing you have to do online, sort of, is the measuring the fragment size. So it's not a very complex thing from the defender point of view. That's what it needs. It needs to run the electrophoresis and declare something. It doesn't need to do anything else. So that's an advantage. And so as we said, he places the seals on the test tubes, marked as S and C. The police covers the seal marking so it wouldn't be entirely obvious. Randomly selects one of them, gives it to the user. Then he removes the seals without removing the cover. You have to be able, the police has to be able to check that later on. Finds the identity of the challenge, commits to it. Now the police removes the cover so the defender can check his marks that it's indeed his own, and only then if everything is okay, then he decommits, he opens his commitment. So it's a mixture. You can see it as a mixture of a physical protocol and a digital protocol. We do have a commitment. You're committing to a value before you are opening it. So this is the protocol, and now you have to repeat it many times to reduce the error. And the resulting protocol is physically complex. And there are many physical assumptions we need to trust: non-forgeable, tamper evident, highly dependent on the party observing it to ensure a correct sequence of operations. It's not the best protocol. It's not a protocol I would want to implement. So we want to do something better. We want a protocol where all the police does is observe from the outside. It never touches anything. But we assume that the defender has a lab and you can observe what they're doing, but you don't need, the police doesn't need to touch anything. Police never needs to touch the suspect's DNA or a tube containing the suspect's DNA. That's certainly better. And the verifier, the police, in particular, right, in the previous protocol, the police handles the input in private. It's not something you want them to do. Okay, so as I said, we want public observation protocols. And nothing is really physically concealed here in this assumption. And those of you who know it, you can think of it as the physical analog to public coins protocols. It's going to be somewhat important to us, but that's a hint for the future. And so here is the point. Look at it this way. Let's look. We have two vectors, right? The suspects. We said that a profile is a vector of length 13, at least in the US. So we have a vector S1 up to S13, and the profile vector is C1 up to C13. And we are going to assume that they're homozygote, that we don't have the issue of two chromosomes, otherwise it wouldn't be as nice as this. And now, if we look at them as together as a set of things, if we look at it as a set of things, then if they're equal, then as a set, it's of size 1. If they're different, it's a set of size 2. Now we're going to amplify. Physically we'll do it, but think of it right now as logically. Repeat it many times. If we repeat it many times, k times, then either the one set becomes stays as a set of size 1, whereas the set of size 2, repeat it many times, where we can choose either from S or from C, it becomes a set of size 2 to the k. So now what the police wants to prove is that the set is large. Not the police, sorry, the defender wants to prove that the set is large. And he should fail if the set is of size 1. If it's of size 1, he should fail. If it's large, he should succeed. That's our goal. And the idea now is to use the Gold versus Sipser set lower bound. So there are all sorts of problems there in using it, but let's first see what it is. So here's the logical protocol. So we have this profile, these two profile vectors, and we said that either it's large or it's small, and we're going to repeat it 2 to the k times, and then we will have to do something physical here. And so how does the protocol look like? We have a subset of 0, 1 to the n. And we want to prove that it's large, way larger than 2 to the m. So the way we do it is we assume that we have a universal 2 family, which is something that already Benjamin mentioned. Ben or Benjamin? Either one. Either way, science wins. So, so you choose, you have such a family. V selects a random member of the family and sends H. P selects Y, such that Y belongs to T, and H inverse of Y is, and H of Y equals 0. Okay, and sends Y and a certificate showing that it's indeed in the set. And V accepts if indeed H of Y is 0 and Y, the certificate indeed proves it. This is the Gold versus Sipser set lower bound from 86. And why is it zero knowledge? I mean, okay, completeness, it's not perfect completeness, but high completeness. Soundness, well, if the set is very small, you're just not going to be an inverse for Y, for 0. And you can show it from using simple properties of universal 2. But why is it zero knowledge? Essentially, the sort of the simulator for zero knowledge is to choose a random Y in T, and then choose a random H, a little h in capital H, such that H of Y prime equals 0. So this is the property you need from the family that you'll be able to do it. And this is what the simulator does. And you can show that it's indistinguishable from random. So now, how does it, what are we going to do here? Now we want to look at the physical analog here. So we'll have the preparation phase. We can expand them. We can create. We can easily physically duplicate things. That's not much of an issue because we can have several tubes. And the problem is that it's not zero knowledge because we're going to reveal one from every tube, something like that. It's not going to be, it's really not going to be zero knowledge because we're revealing something. So what we want to do is essentially do something a little more complex. We want to use, we haven't used something physical yet. Remember we had the PCR, we had the primer before the, we had the primer before the single tandem repeat, before the STR, we had this, 2 strings that we knew what they are. We could make these of random length. We have the power, in this case the defender, we have the power of choosing a random prefix. We don't have to choose exactly these 100 things. It can be either 99 or it can be a little higher. This allows us, this gives us power to make the whole thing zero knowledge. So we're going really to transform z to the k to r plus z to the k. And it's not going to change the size of the set. That's the important thing. By adding a random value there, it's not going to change the size of the set. So we're still going to have 2 sets of this certain kind. But we're now going to do the addition, modular addition. We have to set up the electrophoresis mechanism to report only modular additions. So what we'll do is we'll prove that these 2 sets are large, and we'll prove it by not giving you by not giving exactly what it should be, but the modular values. And that's how we prove the. This is how we prove the. This is how we randomize and how we prove that the 2 sets are large. Oops, what did they do? Okay, good. So this is essentially the protocol. Perhaps, yeah, I guess I should finish. So the hardest part here is really modeling the physical protocol, arguing that they correspond to how do we map the physical protocol to ideal functionalities so that we'll be able indeed to provide a proof. This is more of an art. This is perhaps the place where we can really fail because our translation is incorrect. Maybe we can slip in a card that we didn't think of before. We need to, so this is so the whole thing, it's not infallible. This is the place where we can fail in translating the physical operations into logical operations. Okay. So as we said, the main differences from standard zero knowledge is there's no witness. The ideal functionality really performs the verification on its own. The verify can forcibly cheat. The police can simply break in and take everything with them. There's nothing in the model that prevents them from doing it. And there are all sorts of things you can do. I mentioned a few of them. And I think, I hope I convinced you that physical cryptography is relevant, it's fun, and it can be rigorous. The fact that we are not in the digital realm but working with physical objects doesn't mean that we have to give up all the rigor that we developed in theory. And it's also structured, and there are connections with known crypto and complexity techniques. Thank you.